Abstract algebra. I think it's the most beautiful thing in science because it's pure thinking and you make progress while thinking. Even number theory is not this beautiful. And because number theory, you need to, for example, if you want to explain a theory or number theory, is like half words and half equations. But it needs lots of description. But this is completely abstract and it's beautiful. And it makes progress and it's useful. So that's, I think, is the most beautiful thing in science. Chapter 1, numbers. Well, we're just going to skip. I'm not going to waste time on things that we already know. Z, which is the integers, natural numbers, ordinary numbers. We all know that. Oh, this is very beautiful. Okay. Rules for an order relation. Rules for an order relation. Reflexivity. X. Transitivity. I don't know how to pronounce that. X, Y, and Y, Z, then X. Transitivity. Antisymmetry. We skip some of the proofs, but we're going to come back to it later if we need it. For example, proposition 1.1 is squeezing. If reflexivity, transitivity, antisymmetry. It sandwiches these two things. These are real numbers. Then x equal to z. I think this is not a complete definition. If this is squeezed, all of them are equal. It's not just x equal to z. So this is a typo. I need to point it out. I need to write it down. Wait a minute. I will come back in 2 seconds. Wait, or 3 seconds. It depends how much does it take I find my pencil. So this is not a complete. Wait. X. Yeah, it's not complete, this logical inference, because you can say that x is z and z is x. So based on transitivity, x is equal to z. This is, I think, yeah, this is antisymmetry. And you can do the same thing for y. Like, you can say that x is y, y is x, so x is equal to y. So these are equal to. So from these two, we get this. Bell ordering principle, we had it from number theory. Every set, which is like natural numbers including 0, they have the least elements. That's the Bell ordering principle. And the proof is by proof by contradiction. Each non-empty subset of subset S of n has the least elements. So every subset S of n has the least element. There exists a least element of infinitum of S. Means that least element of S. N plus 0 is almost the same. It's the same thing too. The induction basis, the induction step, principle of induction states. We have done this before. We're not going to do it again. Divisibility. So this is some of the elements of number theory. You see, your brain is using energy right now. The set Z of integers is a subset of set R of real numbers. So integers can certainly be compared using the order relation for real numbers. However, in many cases, different relations between integers is more relevant. This relation of divisibility. Given two integers, the integer m is said to be multiple of n. As an example, consider proof that the divisibility relation on Z shares reflexivity R and transitivity T properties of relation on page 2. Proposition 1.4, divisibility on Z is reflexive and transitive. Why? Because M divides M is reflexive and transitive, not antisymmetric. Transitive means like M divides N, N divides P, thus M divides P. It's very easy to prove. Divisibility on N is an order relation. Order relation. Let M, N, and P be natural numbers. Then M divides M, M divides N, N divides P is M divides P, and M divides N, N divides M is M equal to N. This is called order relation, because if it's reflexive, it's transitive, and antisymmetric, it is an order relation. Rules are for an order relation. There you go. The division, oh come on, division algorithm. I don't want to do that. It's again number theory. Consistency, persistency is extremely important in science. Given a dividend A, as in 1.1, and divisor D, dividend A and divisor D in 1.10, where the fuck is 1.10? There's a unique quotient K, as in a unique remainder R, as in such that the equation function holds. 1.14 and 1.4. So there's a unique K and a unique R, such that you can find different K and R's, but there's just unique. There's a unique K in with this condition. Like, first of all, if you take out this condition, you can put so many Q and R's here. There's unlimited numbers. But when you put this condition, there's just one Q and one R with this condition that fits this equation. Isn't it beautiful? For example, 10 is equal to 4, 2 plus 2. That's it. You cannot find 3 minus 2 because it doesn't satisfy this condition. Simple as that. Define a subset. With Euler ordering principle, we're gonna prove it. I'm not gonna waste my time doing the proofs that have already been done. Greatest common divisors. Oh, GCD. Wow, this is number theory again. Greatest common divisor, relatively prime. A positive integer d is the greatest common divisor of GCD of a and b if d is a common divisor of a and b, and if c is a common divisor of a and b, then c is, yes, yeah, these are like, basic stuff. Euclidean algorithm. Common divisor divides linear combination. The common divisor C of integer n and p is the divisor of each integral linear combination ln and p of n and p. Common divisor C of integer n and p, this is a common divisor, C, is the divisor of each integral linear combination ln plus mp. C divides this one too. It's obvious. Euclidean algorithm not only produces GCD-AB, but the required may also be used to execute GCD as an integral linear combination of A and B. Given integers, the algorithm works with a strictly decreasing sequence. Let A and B be non-zero integers. Then the greatest common divisor GCD A and B may be expressed as an integral linear combination of A and B. Example 1, pen, run of Euclidean algorithm. Consider the determination of GCD 7 and 5 with the Euclidean algorithm. The calls to the division algorithm are as follows. 7 and 5. 7 is 1, 5, 2. 5 is 2, 2 plus 1. Then 2 is 2, 1 plus 0. The GCD of 7, 5 emerges as 1. The remainder from the penultimate system 1 to make sure it's going to become so this is the way that they go about it. Let's check. The Euclidean algorithm is about finding the GCD of two natural numbers and also writing it in a linear combination. So 7, 5 is 1, 1, 1, 0, 7, 2, 5, 2, 5, 2. Then 5, 2 is 2, 1, 1, 0, 2, 1. And 2, 1 is 2, 1, 1, 0, 1, 0. I need to write this again. This is like using the matrices. We go ahead and come back again. Times and these are number theory. It's not algebra that much. Then we go back. 1, 0 is equal to 0, 1, 1 minus 2, 2, 1. Then 2, 1 we write 2, 1 in the form of the, I mean it's the inverse of this matrix, simple. It's 2, 1. This is the inverse, yeah. 2, 1 is equal to 0, 1, 1 minus 2, 5, 2. This is a very clean way of doing it. I like it. I like it a lot. And 5, 2 is 0, 1, 1 minus 1, 7, 5. So what we do here is we're going to write the GCD as a linear combination. How? Linear combination of the 7 and 5. How? This is the basic, this is the starting point. 2, 1. 2, 1 is this. 5, 2, 5, 2 is this. So we are going to end up with 1, 0 is equal to 0, 1, 1 minus 2, 0, 1, 1 minus 2, 0, 1, 1 minus 1, and 7 and 5, which is going to be equal to minus 2, 3, 5, minus 5, 7 and 5. The first line gives 1, minus 2, 7, plus 3, 5. Simple as that. So the GCD of 7 and 5 is 1, and the linear combination is this. It's beautifully written. Beautiful, beautiful, amazing. I loved it. A little bit of patience, you see the beauty of math, as Mariam Mirzakhani said. Well, this is just 16 minutes. I need to continue. Primes and irreducibles. We define a positive integer p to be irreducible if p is greater than 1 and so what's the difference between being irreducible and being a prime? I don't understand it. Wow, it's the difference between irreducibility and being a prime. But the definition is different, but I don't think there's any difference. So it means that if D, this is the definition of irreducible, divides P, then D is 1 or P. This is the definition of irreducible. Like a number 5, which is divisible by 1 and 5. But the prime is, like, if the P divides AB, then AB, then P is A or P is B. For example, 5 divides, I don't know, 20 by 2. In other words, it divides 5 to the 8. So 5 is 5. 5 is yeah. There you go. Prime is irreducible for integers. Irreducible is for positive number. Irreducible. I have no idea how to write it. But my question is, what's the difference between irreducible and prime? So we have primes, we have composites, which is like, the multiplication of primes, and irreducible. How do you write irreducible? Irreducible. I didn't get it. What's the difference between in the ah the difference between irreducible and the primes is irreducible can be 1, 2, but prime is not 1. Prime is starts. Primes are bigger than equal to 2, but irreducible is greater than equal to 1. That's the difference, to the extent that I understood. Irreducibility is an internal or local property of a positive integer p, only involving the finite set of positive divisors of p. That's just like a pure mental masturbation. I don't see any differences between irreducibility, internal property, and prime and so these are both are both are greater than or equal to 2, greater than 1, and greater than 1, 2. But I don't understand what's the difference between irreducibility and primes. The writing sucks, man. I need to check it. Just like pure mental masturbation. An integer n is said to be composite if n, but it's not as a prime. There you go. The fundamental theorem of arithmetic. These are just number theory, man. Wow, that's a lot of exercises. Beautiful. Love it. But I'm not going to do study projects too. Functions. Oh, I'm going to get to the functions. That's amazing. And then equivalence, then groups and monoids. Amazing, amazing, amazing.